Hey, what's going on? I'd like to talk a little bit today about light. In the end, what we're going to get to is Snell's law. We'll talk about how light acts in a material and how that affects how it moves when it transfers between materials. So to do that, first we're going to talk a little bit about the speed of light in a material, and then we'll talk about different models about how that might change things, choose one, and show how that interface change actually works. A couple of weeks ago, we already talked about light as an electromagnetic wave. We ended the electromagnetism chapter about that. As far as physicists are concerned, anything that is an electromagnetic wave is light. We don't really make that distinction very much. It's just a different frequency of the same phenomenon. Although visible light, the visible spectrum is a very small band. We've looked at drawings of that, where that band actually is, and so forth. Last time we talked about some problems with that. We talked about the nature of light itself, how, yes, Thomas Young's experiment showed through the double slit experiment, it showed that light interferes with itself. And that was a really good idea, or a really good demonstration of why light is an electromagnetic wave. But there were some issues with that. One of those was obviously that nobody could identify the thing that the light actually oscillated in, right? A water wave oscillates in water or at the surface of the water. There are pressure waves in water, just like there are pressure waves in air, but those oscillate in water and in air. Similarly, there are waves on membranes. That's how a drum works. Again, all of those things have some medium. Well, light does not have a medium, and that was an issue. And there was one more issue, which was called the photoelectric effect. It had some differences we found from the thermoelectric effect, which is an entirely classical phenomenon. It turns out that light has a quantum mechanical particulate sort of nature, and that gave us photons. That was what Einstein got his Nobel Prize from. And that justifies us using the idea of a light ray, which is basically just a bunch of little light particles, a bunch of little photons, marching together in a straight line, just like little Napoleonic soldiers, doing exactly what they're told, all doing exactly the same thing. When the light hits something, it will move. They will all move at the same point, just like a column of soldiers would. And obviously, we know that the speed of light is 3.00 times 10 to the 8th meters per second. That's a constant that you should know. Probably I'll give it to you on a test, but probably you should know that just as a general sort of educational issue, general knowledge. That's something everybody should know. Like I said, 186,000 miles per second. It's not just a good idea, it's the law. So that is where we're starting out. Now we want to look at what happens in a material. So photons in a material are actually going to move more slowly, right? And you may have heard of it. You may have heard of people stopping light in the middle of a crystal, and they do that through a nonlinear crystal. But that's not really that surprising that you can do that. I mean, you need to have a very special crystal. You need to have a very intricate setup to do it. But photons already move more slowly in the material, and if you're clever enough, you can actually stop them or make them go backwards. You can do all sorts of things if you're a clever materials engineer. So in vacuum, we say that the photons move at the speed c. In the material, they move at a different speed. This is sort of what happens, is that as your light propagates, it'll be absorbed by an atom at some point, and it'll stay there for a little while, and then it will be emitted by that atom. And it'll keep on doing that, one atom at a time, and basically just end up going more slowly than the regular light would itself. And the ratio of the speed of light to the speed of light in the material is the index of refraction n. And so that n has to be greater than 1, obviously, because the speed of light in the material has to be slower than the speed of light in vacuum. Therefore, you've got a bigger number on top of a smaller number. It's smaller than that. So this entire physical rationale is why light moves more slowly in a material than in a vacuum. Not completely surprising, not something that I think you're going to be too scared about. So that just explains what's happening with that index of refraction. We're going to find that that index of refraction, that idea that light moves more slowly in a material, actually has some consequences. Okay. I'd like to look at this in one more sort of physical analogy, a mechanical analogy as well. But in a second, we're going to talk about how this slowing down changes how light acts when it gets to an interface between two materials. So the mechanical analogy I'd like to look at are these two rolling balls. One's going to roll up a ramp, one's not. Although they start at the same speed, they're going to have a different outcome, right? Because as the ball rolls up, it starts slowing down. Obviously, it also has to roll up the slope there, but it slows down, and so the first ball gets a larger and larger lead, and then at the end, the smaller ball sort of catches up to the same speed. It doesn't actually catch up, but it comes back to the same speed, and it always stays a little bit behind. And the same thing would happen with a photon. If you had a light beam directly incident on a crystal, it slows down and then will speed back up after it comes out of the crystal. Not very surprising. We can use our conservation of energy, which, by now you're an expert with, to figure all that out. Basically, you end up with, that original kinetic energy being partitioned when the ball comes up here between a smaller kinetic energy and a potential energy, and that gives you the mechanical analogy. That should be more or less sufficient. It's the same sort of idea. I'm going to use this in a second and compare it to a different principle as well when we talk about a deflection of a ball later on. Here's an example of how you might use this. So you want to find something interesting, like what sort of delay does sunlight give to the light shining through, your window, like this window behind me, or behind you, I guess, behind the computer. So to figure that out, I need to know a couple of things. I need to know the window thickness. It's about 3 millimeters, and the index of refraction of glass, which is about 1.5, is what I looked up, partially because it's an easy number. And so now we can use this to figure out more or less the difference in those times. So first we have to figure out the time if there was no glass, and it's just the same way we did in kinematics. We have a distance divided by a velocity, and that velocity is c, right? So we have 3 times 10 to the minus 3 meters, 3 millimeters, divided by 3 times 10 to the 8 meters per second. That's equal to 1 times 10 to the minus 11 seconds, or 10 picoseconds. Doesn't take light very long to go through the distance of a glass pane. So let's see, or the thickness of a glass pane. So let's see what happens with glass. Well, we have, for the velocity now, instead of c, we have c over n, which means we have that n, the index of refraction, times d over c, which is about 1.5 times whatever we found before, right? Because otherwise it's just n times d over c. We found d over c already. That's 15 picoseconds. That means there's a delay of 5 picoseconds. Reasonable. That's very reasonable. That's something you should be able to figure out. So I think we're okay with that. I have a comparison here. A 3 gigahertz computer adds 2 integers in about 300 picoseconds. So that's not very much time at all. All right. So the takeaways there are really just that the index of refraction is the ratio of the speed of light in vacuum to the speed of light in the material. That's going to change for each material. You'll have to look up the values for different materials. That's the way life works. Basically use the numbers in your book if you can. If a problem says use what is this, use the numbers in your book. That's probably the best idea. So that's the first part of what I'd like to talk to you about. There are some other things I'd like to talk about first, but it's already been about 10 minutes. So maybe it's time to get a drink or, something like that. Go over your notes, make sure everything's fine, and we'll come back to this in just a few minutes. All right? See you soon.